or reaction mechanisms and named reactions you may encounter in A-level chemistry exam, organic chemistry. The first reaction is the radical chain reaction. This is the reaction of alkanes with chlorine using UV light to make halogen alkanes. And this is because alkanes are fairly inert towards most reagent. So this is a photochlorination of alkanes to give you chloroalkanes. This reaction has three steps. The first step is the initiation step. The initiation step is the step when the free radical is formed from the chlorine. So you have the reagent here is chlorine. The reaction conditions here is the use of the UV light to make the chlorine-free radical. This is the initiation step. And then we have the propagation step, and the propagation, it's the step where more free radicals are being produced. So the chlorine-free radical that has been produced will react with neutral molecule in the reaction mixture to make more free radicals. So we have the chlorine reacting with the methane to give you the methyl free radical and hydrogen chloride. And then the methyl free radical itself can react with another molecule of chlorine to give you chlorine free radical and methyl chloride. As you can see in the propagation, each time you are generating more free radical. And this step will continue to generate more and more free radicals as long as there are neutral compounds. And then the termination reaction, the termination step, in which the free radicals that has been produced will react together to give you the final neutral compounds. So you have chlorine free radical and you have the methyl free radical react together to give you methyl chloride. And then you have the methyl free radical can react with another methyl free radical to give you an ethane. You have the chlorine free radical react with another chlorine free radical to give you chlorine. As you can see in the termination step, all the products are just neutral compounds. No more free radicals are produced here. Remember that for this reaction, if you want to get mainly the mono substituted alkane, then use excess of the alkane. Because if you use excess of the chlorine, then you're going to end up with more mono di-tri substituted alkanes. So you could, if you use methane, you could end up with chloromethane, dichloromethane, trichloromethane, tetrachloromethane, and so on. So depending on the reaction condition, it's whether you're going to have mainly one product or mixture of products. An example also of the UV or free radical chain reaction is the reaction of CFC and its effect on the ozone layer. We know that CFC makes holes in the ozone layer because it reacts with the ozone and change it into oxygen. So CFC, which is the chlorofluorocarbon, under the effect of the UV light from in the upper atmosphere, that will give you the chlorine free radical and CCl2F free radical as well. The chlorine free radical is the important free radical here because the chlorine free radical can react with the ozone to give you oxygen and ClO free radical. Then the ClO free radical as well can react with the ozone to give you oxygen and the chlorine free radical again. As you can see, the overall reaction, we have three molecules of the ozone, two molecules of the ozone gives you three molecules of oxygen, and chlorine here only acts as a catalyst, is not added to the oxygen, it's just a catalyst. The second reaction is the nucleophilic substitution reaction. Nucleophilic substitution reaction is the type of reaction which we see with halogen alkanes with different nucleophiles. So the first one is the reaction of halogen alkanes or alkyl halides with sodium hydroxide to make alcohols. Remember that sodium hydroxide can act as a nucleophile or as a base to give you different products with halogen alkanes. That will depend on the reaction condition. So if you heat with aqueous sodium hydroxide, then the hydroxide ion will act as a nucleophile and the halogen alkane will undergo substitution reaction or nucleophilic substitution reaction. So we have the OH, which is the OH ion from sodium hydroxide. It has a negative charge. It has three lone pair of electrons. And then this is the nucleophile. The nucleophile is a species that has electrons a free loan of electrons, or it has a negative charge. And it will attack an electron deficient atom. An electron deficient atom here is the carbon adjacent to the chlorine, because this is partially positive and the chlorine is partially negative. Remember that when you draw your mechanism, the curly arrow always indicates the movement of electrons. So it will go from the electron toward the electron deficient atom. Regardless, whatever that electron deficient atom, it could be a carbon, and also it could be a hydrogen, depending on your mechanism. So now you have your first movement of the electrons, where the electrons on the oxygen lone pair of electrons is going to attack the carbon. So the curly arrow will go from the lone pair of electrons toward the electron deficient carbon, or partially a positive carbon. At the same time, the bond between the carbon and chlorine will break, and the electrons will move from this bond towards the chlorine. Remember that, and this is very important rule, that carbon will never ever form 5 bonds. So the maximum number of bonds for a carbon is 4 bonds. So if you add or attack a carbon with something with a nucleophile, then the bond between a carbon and another atom has to break at the same time, because carbon cannot make 5 bonds. So this is why when the nucleophile attack the carbon, at the same step, the carbon-chlorine bond will break, and this will indicate the movement of electron. That will give you a substitution product, which is the alcohol, and then we're gonna have the chloride ion. Remember that you used sodium hydroxide in this case, so the final side product is going to be sodium chloride. Also, reaction of halogen alkanes with cyanide is another example of nucleophilic substitution reaction. The mechanism is exactly the same. The nucleophile is just different. Now, for the cyanide, the carbon is the one that has a negative charge. So it has lone pair of electrons and a negative charge. Now, this is going to attack the carbon, which is partially positive. At the same time, the bond between the carbon and bromide will break. We do this reaction by reflux in ethanolic potassium cyanide or sodium cyanide. That will give you the product, which is the nitrile substitution product, and then we have the bromide, which is the negative charge, which has the negative charge, or the bromide ion. Remember that you used sodium cyanide or potassium cyanide, so again the side product is going to be sodium bromide or potassium bromide, depending on which one you've used at the beginning. Another example is a reaction with ammonia, and ammonia is again is a nucleophile. This is to make aliphatic amines. So again, the same exactly same mechanism, just a different nucleophile. You have the nitrogen from the amine from the ammonia. It has a lone pair of electron. It's going to attack the carbon, the partially positive carbon. At the same time, the bond between the carbon and the bromine will break. So the curly arrow goes from the bond toward the bromine. Now, once the ammonia has attacked the carbon and made the new bond, the nitrogen will have 4 bonds, so it's going to have a positive charge. So the next step is the deprotonation, so we can get the the neutral compound, or the primary amine, as a neutral compound. So again, you have excess of the ammonia, because this reaction is the condition of the reaction that you use excess ammonia for this reaction. So you have ammonia now that can act as a base. So at the beginning, the ammonia role here was a nucleophile. In the second step here, the ammonia acts as a base, and the ammonia will attack the hydrogen on the one of the hydrogens on the nitrogen. At the same time, the bond between the nitrogen and the hydrogen will break, and it will go towards the nitrogen. So now the nitrogen will regain the lone pair of electron, and you're going to have an ammonium ion. Remember that you also had bromide leaving in the first step, so the final side product is going to be ammonium bromide. Also, remember that in this reaction, you will not end up with only one product, which is the aliphatic amine, but the aliphatic amine that has been formed still has, the nitrogen still has a lone pair of electron, and it still can act as a nucleophile. So it can attack another one of the alkyl bromides or the halogen alkanes. So it will give you a secondary amine. And the secondary amine, in the same way, also the nitrogen will have lone pair of electrons, can act as a nucleophile to give you the tertiary amine. And the tertiary amine also can form quaternary ammonium compound. The quaternary ammonium compound then that forms at the end is not going to have any lone pair of electrons on the nitrogen, so it's not going to act as a nucleophile. So you're going to have mixture of all of these ammonium compounds, not only the primary amine. Elimination reaction. Elimination reaction is a reaction when you remove a small molecule from your compound in order to make alkenes. So you could either remove hydrogen halide from halogenated compounds to make alkenes, or you could remove water as a dehydration from an alcohol to make alkenes. So the first reaction is synthesis of alkenes from halogen alkenes. Remember that I said that when you use sodium hydroxide or potassium hydroxide, the hydroxide ion can act either as a nucleophile for halogen alkanes to undergo substitution reaction to give you alcohols, or it can act as a base and that will give you an alkene. The reaction condition to make the alkene is to heat with ethanolic potassium hydroxide or sodium hydroxide. If you heat with aqueous sodium hydroxide or potassium hydroxide, the hydroxide will act as a nucleophile in this case, and you're going to end up with the substitution product, which is the alcohol. So the mechanism here is different from the substitution. So you have the hydroxide ion, which is negatively charged. The oxygen has a negative charge here, has 3 lone pair of electrons. The OH is going to attack, acts as a base, so it's going to attack the hydrogen on the adjacent carbon. So this is the carbon which is attached to the bromide, and this is going to attack the hydrogen on the adjacent carbon. At the same time, the bond between the carbon and hydrogen will break, and these electrons will move to make the double bond. Remember, carbons cannot make 5 bonds, so at the same time, the bond between the carbon and the bromide will break. So there are 3 curly arrows here. So the final product here is going to be your alkene, where there is a new bond has been formed, and then you have water, which is the OH with this hydrogen, and then you have the bromide ion. The bromide that has left now can react with the sodium or the potassium, depending whether you use sodium hydroxide or potassium hydroxide, to give you sodium bromide or potassium bromide. Another elimination reaction with a different mechanism is the synthesis of alkenes from alcohols. This is called dehydration reaction. This is a specific type of elimination. This is called dehydration because we remove a molecule of water. And to achieve this reaction, you need to heat with either concentrated sulfuric acid or concentrated phosphoric acid. The acid here will act as a source of a proton for the first step of the reaction. So in this reaction, you have the hydroxide ion, which has the lone pair of electron. This is neutral. And then you have the proton from the acid. The first step is that the lone pair of electrons or the oxygen will attack this proton. And this will give you the first the first intermediate in your reaction, where you have the oxygen, which has 3 bonds now, 2 hydrogens from in the alcohol, and the oxygen is still attached to the carbon. Now the second step, and it's going to have a positive charge, of course. Now the bond between the carbon and oxygen will break, so the curly arrow will show the movement of the electrons from the bond toward the positively charged oxygen. That will then create a carbocation with a carbon with a positive charge because we broke this bond and the electrons went to the oxygen to give you the water molecule. Now the carbocation that has been formed to stabilize it will make the alkenes, and to make the alkenes the bond between the carbon, the adjacent carbon, and the hydrogen will break, and the electrons will move to make the double bond between the 2 carbons, and hydrogen is going to leave here as a hydrogen plus or as a proton. This is why the sulfuric acid or the phosphoric acid has been used just as a catalyst, because you added a proton at the beginning and a proton has left at the end as well. And that will give you the final product, which is the alkene. Electrophilic addition reaction. So electrophilic addition reaction is the reactions which we see with the alkenes when you add a small molecule to the double bond. Examples of that is the addition of hydrogen halides to alkene. The mechanism of the reaction, this is called electrophilic addition because the first atom that is added or the first ion that is added is the or the first species is the electrophile. So we have hydrogen chloride here. The hydrogen is partially positive. The chlorine is partially negative, as we know. And then we have the electron-rich double bond. The electrons will attack the electrophile or the partially positive hydrogen and the hydrogen chloride. At the same time, the bond between the hydrogen and chlorine must break. So there is another curly arrow that shows the breaking of the bond where the electrons will only move to the chlorine to make the chloride ion. Now you have generated a carbocation. Why? Because the hydrogen was added to one of these two carbons and then another carbon will be electron deficient, so it's going to have a positive charge. This is a carbocation. Now you have the chloride that was left that was generated in the first step. This is a nucleophile which is going to attack the carbon or the carbocation or the carbon with the positive charge. That will give you the final product, which is a halogen alkane. So this product, in this case, we had a symmetric alkene. So when the hydrogen is added, whether it's added to carbon, the first carbon or the second carbon, you will always end up with the same carbocation and you will always end up with the same product. What if we have an unsymmetric alkane? Then we have to consider that the hydrogen could attack any of these two carbons. However, the products will not be of equal proportion. One of them will be a major product and the other one will be a minor product. So we have hydrogen bromide here, and then we have the double bond of the alkane. This is an unsymmetric alkane. So we have carbon number 1, carbon 2, and then we have carbon 3. So we have the double bond, first step. The double bond will attack the hydrogen, partially positive hydrogen from the hydrogen bromide. The hydrogen bromide bond will break and the electrons will go toward the bromide. The hydrogen could be added to carbon number 1 or carbon number 2. So if it adds to carbon number 2, as we can see here, that will generate a positive charge on the carbon number 1. This is a carbocation. This is called a primary carbocation. A primary carbocation is the carbocation that only attach to one carbon. So this is a primary carbocation. The second one, if the hydrogen adds to carbon number 1, here hydrogen added to carbon number 1, the positive charge will be on carbon number 2, and then this carbocation that is generated is called secondary carbocation. It's secondary because this carbon is attached to two other carbons, so this is called secondary carbocation. We know that secondary carbocation is more stable than primary carbocation because of the inductive effect of the methyl group or of the hydrogen of the carbon, where they have positive inductive effect. They push the electrons towards the carbocation or towards the positively charged carbon, so it increases the stability of the carbocation. So in this case, more of the secondary carbocation will be generated than the primary carbocation, which is less stable. So if the bromide attacks the primary carbocation, that will give you the 1-bromopropane in this case, and this is going to be the minor product because less of the primary carbocation will be generated. However, when the bromide attacks the secondary carbocation, that will give you 2-bromopropane, and this is the major product because, as we said, the secondary carbocation will be the one that's going to be generated more because it's more stable. Remember, the second step is the attack in the mechanism is the attack of the bromide. The bromide will attack the carbon deficient or the positively charged carbon. Another example of electrophilic addition reaction is the addition of halogens. Addition of halogens is something like bromine. So when you have the double bond here of the alkane, the double bond will attack one of the two bromide in the bromine molecule. We know that bromine, there is no partially positive or partially negative, but when the alkene approaches the alkene, the bromine, it will kind of generate a partially positive and partially negative uh, sides of the bromine. So the double bond will attack one of the bromines and or one of the bromides in the bromine, and then the bond between the other two will the two bromine will break to give you the bromide ion, and then the first bromide will be added to the double bond. The second step is that the bromide with a negative charge will attack the carbon with the positive charge, and that will give you the dibromo product or the dibromo alkane. Addition of water. This is a specific type of addition reaction, and it's called hydration because we add water molecule. In this reaction, we use a sulfuric acid here as a catalyst to add the water molecule. So the mechanism of the reaction, you're going to find that we don't simply use a proton to add to the double bond, but we use the sulfuric acid. So the first step is going to be the double bond between the two carbons will attack the hydrogen on the sulfuric acid. At the same time, the hydrogen oxygen bond of the sulfuric acid will break. The second step will be the generation of the carbocation. The hydrogen will be added to one of these two carbons in the double bond, and then also we're going to have the sulfate ion with the oxygen that has a negative charge. The sulfate ion will then attack the carbon or the carbocation or the carbon with the positive charge. That will give you an intermediate of the ethyl hydrogen sulfate. So simply the sulfate ion will be added to the alkane, and then the second step is that you warm with water. Will water simply substitute the sulfuric acid from the alkane, and a hydroxide ion is then added here to give you the alcohol, which is the ethanol, and then the sulfuric acid is regenerated again. This is why sulfuric acid only acts as a catalyst here, because it's regenerated at the end of the reaction, and you end up with your product as ethanol. Nucleophilic addition reaction to carbonyl. So when you have an aldehyde or a ketone, a nucleophile can add to the carbonyl group. This is a nucleophilic addition. This is different from the electrophilic addition that we found with the alkenes. We're going to see why we call this nucleophilic addition. Nucleophilic addition because here the nucleophile is the one that is going to attack the partially positive or electron deficient atom. So we have the carbonyl group. We have the carbonyl group where the oxygen is partially negative and the carbon is partially positive. So now you have the cyanide. We add cyanide here. So we have the cyanide, which is the nucleophile. It's going to attack the electron deficient or the partially positive carbon. Remember, carbon cannot make 5 bonds, so this is facilitated by breaking off the double bond between the carbon and oxygen in the carbonyl group to move towards the oxygen. Now we're going to have an oxygen, the cyanide has been added, and then we have an oxygen with a negative charge now, so have 3 lone pair of electrons. So if you add water in the second step, hydrogen will be added to this oxygen, so you have water like this. So this lone pair of electron from the oxygen, which has a negative charge, will attack the hydrogen to give you the final product, which is the cyanohydrine. So you simply added the cyanide to the carbonyl group. Elimination reactions. So addition elimination reaction is the type of reaction or the mechanism where we find two things happening in the same reaction. This is first step is an addition. The second one is an elimination. The overall reaction will be a substitution. But actually, what we call this mechanism is addition elimination. We will find this type of reaction in reaction of acid chloride or acid anhydride with nucleophiles. The nucleophile can be either alcohol, amine, or water, and the product will depend on the nucleophile we've used. So what is the mechanism of the reaction? The first step, you have the alcohol. So let's say we are going to react an alcohol with an acid chloride. The first step again is a nucleophilic, will be an addition reaction in the same uh, way we found it in the addition to the carbonyl. So we have the carbonyl group and the acid chloride. The lone pair of electrons on the oxygen for the alcohol is going to attack the partially positive carbon. At the same time, the bond between the oxygen and the carbon will break and double bond to give you an oxygen with a negative charge. Now, the second step, this is the addition step. The second step will be the elimination step. In the elimination step, the chloride is going to leave, so the bond between the carbon and the chloride will break. At the same time, the electrons on the oxygen will then move to make a double bond between the oxygen and the carbon. That will regenerate the carbonyl group again, and then you're going to have an ester. But remember that the alcohol that attacks the carbon in the first step and the addition step will have three bonds, so the oxygen will have a positive charge. Remember that the chloride has left as the chlorine has left as a chloride ion, so this the second step will be the deprotonation. In the deprotonation, we need to generate the neutral compound or the ester that is going to be formed here. So the chloride will attack the hydrogen to deprotonate the oxygen, and at the same time the bond between the oxygen and hydrogen will break and the electrons will move towards the oxygen. That will give you the final product, which is the ester, and then hydrogen chloride will be generated as substitution product. In case of using amines, you're going to end up with amides, and if you use water, you're going to end up with carboxylic acids. Esterification. So esterification is the formation of esters from acids and alcohol. Even though they don't want you to know the exact mechanism for the esterification, you should know the name of the reaction, which is the esterification, and examples. So if you have any acid, carboxylic acid with any alcohol, and this is acid catalyzed reaction, you're going to end up with the ester, and water molecules will be removed. So this is called esterification. So whatever the acid, the carboxylic acid and the alcohol, just generate a new ester bond and remove a water molecule. Again, this is benzoic acid with a methanol that will give you methyl benzoate, for example. Hydrolysis. Hydrolysis is the formation of alcohols from esters. So if you have an ester and then you add water and use an acid catalyst, then you can the ester can break down to give you the carboxylic acid and the alcohol. This is called hydrolysis, and because we used water to break a molecule. And this reaction can be either acid catalyzed, where you use an acid as a catalyst here. In this case, you're going to use water molecule as there are, or it can be base catalyzed hydrolysis. In this case, you're going to use a base and you're going to use an OH minus as your base, like sodium hydroxide or potassium hydroxide, and reflux with the base. That will give you the salt of the carboxylic acid and the alcohol. If it's acid catalyzed, that will give you the carboxylic acid and the alcohol. But if it's base catalyzed, that will give you the salt of the carboxylic acid. So if you use sodium hydroxide and ethanoic acid, it's going to be sodium ethanoate and the alcohol. Saponification is a specific type of hydrolysis of esters, but in this case, this is used to make soap by base catalyzed hydrolysis of fat. So we know that fats are triester of glycerol, triester of glycerol for fatty acids. So this, if we heat with sodium hydroxide, this is going to, the triester will undergo hydrolysis in the same way like any ester to make this is base catalyzed, so it's going to make the sodium salt of the carboxylic acid. But the acids here is fatty acid, a long chain fatty acid. So the sodium salt of the fatty acid is the soap that we use. This is why this reaction is called saponification, and it's used to make soap. We have the glycerol. This is the alcohol that is generated from this hydrolysis or from this saponification. Friedel-Crafts acylation. Friedel-Crafts acylation is the reaction when you add an acyl group to benzene ring. So it's a type of a substitution reaction. So if you have your benzene ring, for example, like this one, and then you have the, for example, methanoyl chloride, so acid chloride, you add the acyl group, so you end up with the addition of the acyl group COCH3, so you end up with a ketone. And if you use formoyl chloride or methanoyl chloride like HCOCl, then you're going to end up with the benzaldehyde. So the mechanism of the reaction, there are two steps. For this reaction, we need to use the aluminum chloride as a catalyst. Aluminum chloride will act as a catalyst to generate the carbocation or to generate the electrophile. The electrophile that is generated from the, for example, this is ethanoyl chloride with aluminum chloride. The chloride will attack the aluminum while the bond between the carbon and the chloride will break. Now this will generate the carbocation or will generate the electrophile where the carbon will have a positive charge now. And then you're going to have you can either write it as AlCl4 and all minus, or you can simply write it in this way. And then the second step will be the attack of the electrophilic attack. So you have your electrophile here and you have the electron-rich benzene ring. So the electrons will attack, or the electron-rich benzene ring will attack the positively charged carbon or the electrophile. That will generate an intermediate in which the ring or the double bonds or the rings inside the electron ring inside the ring will open, and the benzene ring is going to have a positive charge, and then the electrophile was now added. Now the second step is the deprotonation, the removal of the hydrogen or deprotonation to regenerate the stable benzene ring. So the bond between the hydrogen and the carbon will break to send the electrons back into the ring to make the cyclic benzene ring again. And then we have the deprotonation will be done through the chloride that has been left in the first step from the ethanoyl chloride. So this intermediate, the chlorine, the chloride is going to attack the hydrogen, while the bond between the aluminum and the chloride will then break. We will regenerate aluminum chloride, which is just a catalyst here in this reaction. We're going to have hydrogen chloride from this chloride with the hydrogen, and then we're going to have our product, which is this aromatic ketone compound. Nitration. Nitration is when you make nitrobenzene. So you have your benzene and you warm benzene with concentrated nitric and sulfuric acid to give you nitrobenzene. Sulfuric acid is here acts as a catalyst. So it will make the nitronium ion, which is the electrophile that is going to be attacked by the ring or by the high electron-rich benzene ring. So how is the nitrogen ion generated? So you have nitric acid react with sulfuric acid that will give you H2NO3 plus. So a proton has moved from the sulfuric to the nitric, and HSO4 minus, which is like an ion from the sulfuric acid. And then you have this generated positively charged compound H2NO3 plus will then break down to give you the nitronium ion, which is NO2 plus and water. The reaction mechanism would be exactly the same like the Friedel-Crafts acylation in the second step, where you have the electrophile, you have the electrons inside the ring will attack the electrophile, and then that will break the ring, electron ring inside the ring, um, with a positive charge inside, and then the hydrogen is going to leave here, or the proton, and the electrons will move from this bond towards the ring inside the ring again to regenerate the benzene ring, and you end up with the nitrobenzene as your product, and then you have the hydrogen ion. Reduction. So there are several reduction reactions that you need to know. You don't need to know the mechanism of these reactions, but you need to know the reagents and condition. The first one is reduction of cyanides to make amines. So we have the cyanides reacting with the hydrogen from or reduced by the lithium aluminum hydride, which is reducing agent. The reaction takes place in two steps. The first step is by the use of lithium aluminum hydride, and the second step by the addition of dilute acid. So this is why we write it as 1 and 2, because it's two steps. The final product is going to be the formation of the primary amine by addition of 4 hydrogens to the carbon and the nitrogen. So it's going to give you a primary amine. Remember that this is the only product for this reaction. It's not going to give you mixture of primary, secondary, and tertiary like the substitution of halogen alkanes with the amine with ammonia. Another one is also another example as well is cyanide can be reduced as well using hydrogen molecule with the use of a nickel catalyst under high temperature and pressure that will give you the exact same product, which is the primary amine. This reaction is preferred in industry because lithium aluminum hydride is quite expensive, and the use of the nickel catalyst and the hydrogen is cheaper than using lithium aluminum hydride. And finally, reduction of aromatic nitro compounds to give you aromatic amines. So if you wanna um, um, prepare aromatic amines, no, you can start with nitro compounds, aromatic nitro compounds like nitrobenzene. The reaction condition for this, we use 10 with concentrated acid like concentrated HCl and reflux. And the second step is to use sodium hydroxide. The reason why we add sodium hydroxide in the second step is because what's generated from the first step is going to be the ammonium, quaternary ammonium compound. So it's not just going to be nitrobenzene, it's NH3Cl. So in order to get the phenylamine or the neutral compound